Well, let's take a quick look now back at Unit 2. In Unit 1, we talked about current voltage characteristics outside of the transistor. In Unit 2, we started looking inside the transistor, which is what this course is all about, trying to understand why those IV characteristics have the shape that they do. We began with an energy band picture. We quickly reviewed what an energy band diagram is, and then we discussed how we can understand the current voltage characteristics of transistors in terms of energy band diagrams. And if there is one thing that you take from this course, that's what you should take from this course, because if you understand how energy band diagrams and manipulating potential barriers control the current and result in the transistor characteristics that we see, then you've learned something very significant and that you can take away with you from the course. The rest of the course is really filling in details on that picture. We spent a little bit of time on the traditional theory of the MOSFET as it's been around since the 1960s and 1970s. And it's important that you be able to look at an IV characteristic and say, aha, that's a long channel transistor, and that's a short channel transistor. We talked about that briefly. And then we introduced a simple, compact physical model that we're going to carry through for the remainder of the course. It's called the virtual source model, and we will go back to this in each unit, and we will refine it. By the end of the course, we will have a very simple but highly physical, compact model that helps us understand the current versus voltage characteristics of modern transistors. Well, we began with a quick review of energy band diagrams. An energy band diagram is a plot of the conduction band versus position, or valence band, or intrinsic level. And when the bands bend, then interesting things occur, and we have some type of semiconductor device. We talked about how you read an energy band diagram. So once we have an energy band diagram, then we can read some really important quantities off of that diagram. If we're interested in how the electrostatic potential varies inside the semiconductor, well, it's proportional to the conduction band, or minus the conduction band, or valence band, or intrinsic level. So we just flip one of those upside down, and we have the potential versus position. If we're interested in what is the electric field in this semiconductor, well, that's proportional to the slope of the conduction band, valence band, or intrinsic level. If we'd like to know how the electron density is varying with position, well, that's related to how far above the valence of the intrinsic level the Fermi level is. So we can read that right off the energy band diagram. If we're interested in the hole density versus position, well, the hole density increases when the Fermi level goes below the intrinsic level. So we can read that right off the energy band diagram. And finally, if we want the space charge density, rho, well, we can use Gauss's law, divergence D is equal to rho, but that's going to require us to take a second derivative of the conduction band minima. That can be a little difficult to do if we're trying to sketch this, but we could also do it by just saying if we know how this semiconductor is doped and we've deduced what the hole and electron concentrations are, then we can figure out what the space charge density is. So we get a lot of information from an energy band diagram. Well, these are the IV characteristics of a typical MOSFET. Pretty representative of what we might still see today, although channel lengths are quite a bit shorter today. If we ask, what's going on at low drain-to-source voltages? Well, we can draw energy band diagrams. These are actually computed by a computer simulation. And what we see here is that there's a conduction band in the source. The conduction band in the drain is a little bit lower because a small voltage has been applied to the drain. There's an energy barrier in the channel that controls the flow of electrons from the source to the drain. The positive voltage from the gate pushes the energy down in the channel and allows current to flow. This is the linear regime. The MOSFET behaves as a voltage-controlled resistor. Well, if we look at higher voltages, and ask what's going on there. Why does the current saturate or try to saturate? Well, the energy band diagram looks like this. We've applied a large voltage to the drain and pulled the conduction band minima way down, but current still doesn't flow because there is an energy barrier between the source and the channel. A positive gate voltage pushes that energy barrier down and allows the current to flow. And you can see that what's limiting the current is getting over that barrier. So applying a larger and larger drain voltage does very little to the current. That's why the current saturates. So it's this simple picture of how transistors work in terms of energy band diagrams, which is really probably the most important concept in this course. So spend some time and make sure that you understand that thoroughly. We're just going to be filling in details of that picture as the course proceeds. One of the additional things that we can now understand is what is DIBBLE, drain-induced barrier lowering. We explained how you would extract that from measured IV characteristics, but what is it about physically? Well, it's very easy to see. If we have an IV characteristic at a low drain to source voltage like this, and at a high drain to source voltage that looks like this, you'll recall that we pick a fixed current. We can see that at that fixed current, it takes some gate voltage. To achieve that current, we would call that the threshold voltage in the linear regime. At a higher drain voltage, that same current is achieved at a lower gate voltage. So we would call that the threshold voltage in saturation. So there are actually two different threshold voltages. That's not a desirable feature. Transistor designers try to make those two threshold voltages as close to each other as possible. And we measure that shift in threshold voltages actually in a slightly different way. We just measure the horizontal translation between these two curves, the change in gate voltage needed to maintain the current at a constant value while we change the drain voltage. Okay. But what's the physics? So we can understand the physics by the energy band diagram. Here's the conduction band versus position at a low drain to source voltage. So the conduction band in the drain is just a little bit lower than the conduction band in the source. We have a big barrier. The device is off, or only leakage currents are flowing. We're below threshold, so no current can flow. If we apply a large voltage to the drain, we pull the energy way down. But if we properly design the transistor, the height of that energy barrier is controlled by the gate and only weakly dependent on the drain. But there is some dependence. You can see the drain is trying to pull that energy barrier down and allowing more current to flow. That's what we refer to as DIBBLE. That is drain-induced barrier lowering. The higher voltage on the drain is pulling that barrier down. We minimize that by proper electrostatic design of the MOSFET, which we'll talk about later, but there's always some amount of that barrier lowering there. That's the physics of DIBBLE. Okay, we also talked very quickly, because it's really quite easy, about the traditional theory of MOSFET IV characteristics. We looked in the linear regime. Here's a cartoon cross-section of the MOSFET. We know that current is charge times velocity. There's a very simple expression that relates the mobile electron charge in the channel to the voltage. You know that charge is capacitance times voltage. That's basic electrical engineering. This is only part of the charge, the part that is due to mobile electrons. So we have to take the voltage above the threshold voltage. That induces this mobile charge. So it's capacitance times that voltage difference. It's negative because these are electrons. This is an N-channel device. So we know the charge. The velocity, well, velocity is minus mobility times electric field for electrons. We have a small voltage between the drain and the source. the distance is the channel length L, so the electric field is drain to source voltage divided by L. Put it all together, we get this very simple and really very accurate representation, mathematical description of the IV characteristic in the linear regime. Okay. What about high drain to source voltage? Well, this requires a little more discussion. So if we apply a high voltage to the drain, then the voltage in the channel is varying as we go from the source to the drain. And the difference between the gate voltage and the voltage in the silicon channel is getting less and less as we go towards the drain. That means we will get less and less charge as we move from the source to the drain. Now you can see from this simple expression that once the voltage in the channel reaches a critical value, VGS minus VT, we won't have any charge left. All right, well, that's a limitation of this simple equation. There actually is a small amount of charge moving very fast that will continue to carry the current. That's called pinch-off. And that plays a critical role in this theory of the transistor. So let's see how that works out. So the mobile charge is in the channel, and when the voltage at the drain end of the channel hits a critical value, the mobile charge goes approximately to 0, and we say the channel is pinched off. Okay. Well, what happens then? Current is still charge times velocity. This applies anywhere. The current that comes in the source goes out to drain, so the current is constant anywhere, so we can pick any location. We pick the location that makes it easiest for us to compute things. And that's the beginning of the channel, back at the source end. Well, we know the charge there, it's just minus Cox Vg minus Vt. Okay? The velocity is minus mobility times the electric field there. What's the electric field? Now here we had to be a little careful because the voltage across this channel, well, at the drain end, it's the pinch-off voltage. If I apply larger and larger voltages, I'm just going to have a very small region there with a higher and higher electric field. That's not really part of the channel. The channel itself ends when the voltage hits VGS minus VT. The length of the channel is just a little bit shorter because it's pinched off, but it's approximately L. So the electric field is VGS minus VT divided by L. Put all of that together, and we get a description of the current for the high drain to source voltage, the saturated current. Now, we've just done one thing that's a little bit wrong. You know, what this field is this is actually the average field in the channel. The field is non-uniform under these conditions, and the field is actually 1/2 of the value of that average value at the source, and that's where we're computing the current. So that explains this factor of 2. So this is a square law device. We have a VGS minus VT that comes from the charge, which goes as VGS minus VT. And we have a VGS minus VT that comes because the voltage at the end of the channel is VGS minus VT, and that comes into the electric field. So this predicts that the current will go as the square of VGS minus VT. Okay, so we've done both linear regime and saturated regime. We also discussed briefly how we could do this continuously from small drain to source voltages to large drain to source voltages. That gives us the so-called square law theory of the MOSFET, and this was basically the first theory of the MOSFET way back in the 1960s when people first began to build MOSFETs. Okay. But if you look at almost any modern day MOSFET, it will not behave that way. These are the IV characteristics of a typical MOSFET that you'll see. As we sweep the gate voltage from a low to a high value, you can see that the drain current goes up and up and up, but it is not increasing as VG minus threshold voltage squared. It's increasing as VG minus threshold voltage to the first power. What's going on there? Well, we discussed that too. It comes from the fact that In very short channel devices, the electric field is very large. Under large electric fields, at least in bulk semiconductors, the velocity saturates at a value called Vsat, about 10 to the 7th centimeters per second. And the carriers just can't go any faster than that. Well, if we want to compute the current, current is still charge times velocity. The charge is still Cox, Vg minus Vt. But the velocity now, because the field is so high, is just the high field saturated velocity, 10 to the 7th centimeters per second for electrons in silicon. You put that together, and it's very simple. We get a simple expression for the current, the saturated current. This would be called the velocity saturated MOSFET. Okay, so that was fairly easy to do as well, but you should spend some time to make sure that you understand that. Now, that all seems very simple. People sorted that out in the 1970s, maybe by early 1980, it was all well known. Is that all there is to it? Well, no. As channels got smaller and smaller and smaller, more and more complicated things happened, and people had to figure out how does that affect the IV characteristics of MOSFETs. So these are computer simulations of electrons flowing through a very short channel MOSFET, done about 20 years ago when 30 nanometer channel lengths were almost unimaginably small. Most of us thought we would never be able to manufacture MOSFETs with channel lengths that short. But today the channel lengths are significantly shorter than that. Each dot here represents an electron being tracked by computer simulation as it moves from the source to the drain. If we go at any point and add up the velocity of those electrons, we can plot out the average velocity versus position. And what you see is that the velocity is higher than 10 to the 7th centimeters per second everywhere. So this involves some rather subtle and complex transport physics. The question is, how does it affect the IV characteristics of a MOSFET? This is one of the things that we're going to want to discuss and see if we can understand a little better as we go through the course. Okay, so we have developed a two-piece model. We have a very nice model of the linear regime, very simple. And we have a velocity-saturated model in the saturation regime. We're a little worried about the physics because we know it's much more complex than that. The velocity in the channel actually doesn't saturate. But for some reason, it seems to describe modern transistors pretty well. And that's part of what this course is about. Why does it continue to describe transistors well? What does this saturated velocity really mean in nanoscale transistors? Well, the actual current is going to be the smaller of the two, and those two currents meet at what we would call the drain saturation voltage. If the voltage is less than that, we use the linear regime. If it's greater than that, we use the saturated model, and we can smoothly connect one to the other and get a smooth characteristic. Okay. We did that through what we called a level 0 virtual source model. So by introducing an empirical function, we could smoothly go from the linear current to the saturated current, and we had a smooth, continuous description of the transistor. We're going to use this model. We're going to come back to it again and again in each unit as we proceed through the course and make it a little more sophisticated until by the end of the course, we will have a model that accurately describes modern transistors in a very physical and simple way. There are only 8 parameters in this model. And so it's really a very simple model, but each of those 8 parameters has a very strong physical significance. We've talked about some of them. The little delta is Dibble. Vsat is the saturation velocity. Mu-m is the mobility. We will revisit this model and dive into it deeper and deeper as we progress through the course. There is one other model, a parameter beta in this empirical expression that connects the linear regime to the saturated regime. But that's typically applies to a broad class of devices and doesn't have to be fit to every specific transistor. Well, the voltages in that model are the actual intrinsic voltages that get into the drain, the source, and the gate. When we attach metal contacts to the transistor, there's some resistance of those metal contacts to the semiconductor. That introduces resistors, series resistors that are inevitably there, and that affects the IV characteristics of MOSFETs. So we talked a little bit about what that does. It lowers the drain to source voltage and the gate to source voltage. And in order to account for the measured IV characteristics and understand them, we need to account for these series resistances. Semiconductor technologists who develop new technologies spend a lot of time trying to minimize these resistances and make them as small as they possibly can. Well, as I mentioned, this model actually does a very good job of representing modern-day transistors. We can get excellent fits to measured IV characteristics just by adjusting a few of these simple, highly physical parameters. We only have to do two things. We have to replace the actual mobility, a familiar concept, by something called the apparent mobility. And we have to replace the high field saturation velocity by something that we'll call the injection velocity. Now, these are not empirical fudge factors that we just adjust to fit the data. They actually have a strong, very clear physical meaning, and we will be discussing what these parameters mean as we proceed through the course. But with those two simple changes, we can take the traditional model and we can represent modern transistors in a highly accurate way. Okay, so that's what Unit 2 was all about. We started with energy band diagrams, and we showed how energy band diagrams can help us understand how MOSFETs operate. That's, as I said, the most important takeaway from this course. But we want to dive a little bit deeper. We dove into the traditional IV theory of the MOSFETs. We discussed briefly how you look at an IV characteristic and say, that's a long channel device. The saturation current increases quadratically with VGS minus VT, or that's a short channel device. The drain current in saturation increases as VGS minus VT to the first power. And we introduced this virtual source model that we will be using as our guide as we dive deeper and deeper into transistor physics in Units 3, 4, and 5. Thank you. I'll look forward to seeing you in Unit 3.